whenever you're given a differential equation like this, there are two ways to proceed. The modern way is you look at this, you stick it on a computer and stare at what comes out of the computer. But it's not necessarily the smartest way. The smartest traditional wisdom in theory of partial differential equations, the first thing you look and you follow Reynolds. Reynolds, and probably people before him, realized that even though this seems to have two parameters, and there might have been more parameters if I stuck them around, but right now it seems to depend on viscosity and length. Maybe there is dimensionless version of these equations in which number of parameters is smaller. So first thing that you always do when you're given PDEs and any real problem, we try to non-dimensionalize, which is a process of getting your equation in a non-dimensional form where number of parameters is minimal, and then it can maybe apply to several realizations. Fluid equations are the best example of it, that you write the equations and then depending on viscosity you can do it in wind tunnel or a small pipe or on a planet or something. It'll be physically the same. So you look at your equations and you have length. So dimensionally, x is length. This is your coordinate. The time is length square. If you don't like this, do it yourself. The field itself has dimensions inverse length, and viscosity, if I'm just using length as the only scale, viscosity has dimensions length square. So basically, if you don't believe me, you just stick these dimensions in here and you make sure that all the terms have the same dimension. So for example, this has two extra derivatives and it has to be same dimension as this term. So viscosity has to be dimension in length squared. Then what you can do is you're allowed now to rescale and produce dimensionless numbers. So you can replace x by, this is length, and multiply by square root of viscosity. Take time, multiplied viscosity. Take u multiplied by viscosity squared. And after you have done this equation here will have a form which is actually a rather elegant form. It'll look like u of t plus, I'll expand this derivative, just looks nicer that way, ux, that's the same as gradient term in convective term here, plus the Laplacian of your field plus Laplacian square is x now being restricted to domain from 0 to length times mu minus 1/2. And now notice this become dimensionless, or it's convenient to write this as 2 pi. This 2 pi will be natural because it's a periodic domain, and when we get to Fourier transform and such, it will be a natural thing. Where the Reynolds number of this problem, or non-dimensional size of the system, is lambda equals the length of the system divided by 2 pi square root of viscosity. So it turns out, well, intuitively, viscosity means something to you because it tells you how strong is the non-damping term. The intelligent way to think about this problem is to get rid of viscosity, basically set it equal to 1, and you just look at the size of the system. So that's what dimensional analysis gives you.